millimeter for crystal under polarized light. So I almost immediately transfer that over to micrometers. That's 30 micrometers, okay? The article displays the maximum retardation value of, so retardation, that's delta, is equal to 1260 nanometers. Okay. Just as a side note, what is the equation for retardation? That is thickness, big N minus little n, or this is also called birefringence. Okay? Okay. I rotated the crystal and was able to measure the refractive index omega. Okay, so omega. You're giving me a lot of information here. 1.6800. Okay. I was able to obtain a slightly off-center interference figure in which I put in the 5-frame compensator. So now it's, okay, so that's what we have, plus one other thing. And so what I need, I mean, what the question's asking for are the RI values. So it wants omega, epsilon. It wants birefringence, and the optic sign. So those are where I need to get to, given from this information, plus some image interpretation. So we got our, I'm drawing center, but it doesn't matter. Here's our nice, so number one, do we have a uniaxial or biaxial crystal?
Union.
Good, all right. We also do that because we're given omega, right? So we know that it's uniaxial. So remember, we also, I like to just draw these lines here. What have I just drawn there?
Omega.
Omega, yep. And what are those? I just got epsilon, but epsilon prime, but yeah. Okay, so that's what I've got. That's essentially a bad drawing of this first image right here. So now I'm going to put in my compensator, and I didn't say anything wonky about how it's oriented. I've always said here, note the slow ray of the compensator is the typical northeast-southwest direction. So that means, okay, that's my slow ray, and I'm saying it's 550 nanometers. So that is essentially the slow ray direction right there. So when I put this in, I see some color changes. So what do I see going on? So you can do any of these areas here, but if you hopefully remember, what happens here happens here. What happens here happens here. But these, whatever happens in these two, are the exact opposite of what happens in these two. Okay, so you can keep those as kind of a check sometimes if you're on your interpretation. Okay? So, what happens when I put this compensator in? Do I get addition or subtraction going on here? In this quadrant here?
That's subtraction.
It's subtraction, yep. I got subtraction here, so if you could actually see, you can actually kind of see this gets milky here, milky there. Okay, so I've got subtraction going on here. What does that tell me?
Go ahead.
I was saying, isn't this only that omega is greater than epsilon if it's negative, or?
Yeah, right. Or what's another? You're right.
Oh.
Okay. Yes.
Oh.
Is epsilon the fast ray or the slow ray? You are 100% right. Just rephrase that. I just think about it differently than you do, but you're 100% right. I'm not challenging you at all. You're right. What does that tell me about epsilon? Is it the fast ray or the slow ray?
Well, if it's parallel with Wait,
This, I'm talking about this vibration direction here.
sorry, okay.
Yep. And I see
So-
subtraction here. What does that tell me?
So wouldn't that end up being the fast way in that case?
Yes, that's exactly right. Yep. Because we don't get addition, right?
Yeah, that's how I was just like
Yep.
confusing the two.
Remember that when the slow ray of the particle or the crystal is parallel to the slow ray of the compensator, we get addition. But in this situation, this was not, well, we're kind of going in the opposite direction here. Since we got subtraction, that's saying that this is not the slow ray. That epsilon is the fast ray, omega is slow. Are we all good on that? We're following everything on that? So, what does that tell me about my optic sign? Yep. Okay, so we got one thing checked off. Okay. Now what the heck do I do?
You get birefringence.
We-
You want to
we-
get the
we like the
birefringence.
birefringence,
Yes.
So how do we do that?
So you just plug in the retardation and the thickness.
Yep. So we're going to start right, we're going to just manipulate this equation here. We
Mhm.
have that value of 1260 nanometers. And that is equal to thickness times birefringence. So 1260 nanometers equals 30,000 nanometers. Right? I converted that from micrometers now to nanometers. Birefringence is equal to 1260 divided by 30,000, which equals 0.042. You following that? That literally we were given, we weren't given this, we were given this. But we always kind of figure out, if you're given something, what's the mathematics behind it? Because then you can manipulate that mathematical equation in your favor. So, we were given this value, the birefringence, or the retardation is this value. I just simply plugged it in there. We were given this thickness up here, plugged it in there, and we calculated this, the birefringence, which is right here. All right. Check that off. Omega we got. So what's my last thing? I need to get this. How the hell do I do that? Yeah. Good. So, birefringence, 0.042 equals big N minus little n. So, who's the big N, who's the little n?
Omega. Because it's negative sign.
Yep, omega is the big one. So it is, and if I just kind of do some rigmarole here, I come up with the end. Is that clear?
Little n.
That's little m. Yep. So, epsilon is 1.638. We following all that? So it's important to understand, like, pretty much anything I'm going to give you, or that we've actually seen in all of the review from last semester and this semester, is some manipulation of this, interpreting this, so we can figure out something to do with, or some manipulation of optic sign, or interpretation of an image. Everything else is just kind of just basic mathematics, I guess you'd say. But it's putting the concepts together, right? The math here, you can all do this in your sleep. There's nothing to really get complicated. it's putting together the concepts that make this challenging. You get that? Are you okay with that?
Yeah, I'm just really mad at myself because after you laid it out, it's so obvious.
It is,
Because I was on the right track, I just got stuck.
but the thing is, you need to make these connections with what you've got, and this goes back to when I talk about like studying for this or, and it's really great. I'm not trying to compare myself to this person at all, but essentially Richard Feynman says the exact same thing, which is when you think you know something, take a step back and ask, well, why or what? Try to get more and more of a fundamental understanding of something, and then you will then truly understand it. And then if you can explain that to somebody else, you truly will understand what they're talking about. Like biofluence, oh, that's the colors that I see when I cross the poles. Well, why is that? Where does that come from? Well, it comes from that. Well, what is that? You know, just you're burrowing your way down to understanding something. And if you get down to the mathematics, then you're rocking. You can't always do that. But
A question.
yeah.
So why at first it's epsilon prime, but at the end you can write epsilon?
Oh, because we have a perfectly centered interference figure.
No.
Yeah.
Oh, well, we don't.
We do.
Oh, we do?
Yeah. Well, no, it's fine.
Okay.
Why?
Oh, I think I know. Like that one is just for in general, and then that one, the biofrequency is it's the omega and
Yeah, I guess
epsilon.
it's
That's why.
Probably.
Because
ever so
yeah, I
slightly
wrote
off,
epsilon prime.
But yeah, you're right. Is that correct? You might be right. It might actually be an epsilon prime because it's probably whatever. So this would be perfect. We're off like this, so you might be right. There might be an epsilon prime. Yeah, now I think about it, you're right.
Mm.
Yeah. Not by far, but you're right.